Okay, Assalamualaikum warahmatullahi wabarakatuh, and good day, everyone. What I'm going to do today is to present my research, or is in my paper. This is the title of Estimation of Bending Natural Frequency of the Seaplane Float on the Water. This paper is written by me, Ibo Nugroho, other colleagues, Kusnindar Priyautomo, Nanang Purnomo, Muria Sugiharto, Pak Doni Hidayat, and Pak Sahlan. All of us is from a research center of hydrodynamic hydrotechnology, except Pak Doni Hidayat from Research Center for Aeronautic Technology. The outline presentation will consist of introduction, theoretical basis, the finite element model, results and discussion, conclusion, and the references. Since Indonesia is an archipelago, the transportation between the island is always important matter. One of the transportation modes is by using seaplanes or amphibious plane, because this plane can land and take off at any place on the seawater. So as in the case study in this paper, in the research, we are using a Seaplane N219A. You see the line span is on the right-hand side below here, and the plane itself on the left side, right-hand side, this one. This float itself is taken from the design of 2091. So when we're doing tests, when they are doing the test of in towing tank in 2091 from the National Aeronautics Institution. As we know, this type of aircraft is often disturbed continuously by turbulence, waves, and so on during takeoff, landing, and taxiing on the water surface. This can easily cause the coupled vibration of the aircraft structure, affecting the efficiency of the system, equipment, and the fatigue life of the structure. Therefore, as a main part of the seaplane structure, the float can be vital to a dynamic characteristic evaluation. It means if we can calculate the natural frequency, then it will be good to know the characteristic of the structure. That will be very, very useful. The theoretical basis. We modeled using the vibration of the floats on the water. We approximated with the simple continuous model to represent certain fundamental aspect of the float vibration. In the equation we apply on the floats, we can assume as a standard Euler beam on elastic foundation with a viscoelastic term in the stress-strain law for the beam material. Is a nu is viscoelastic constant. So FEI is second term of equation is material damping the float structure, where the right-hand side equation Fxt is act as a beam, is represent the vibration excitory with us from seaplane propeller. That's why in the mid we assume that the engine is installed in the mid of the plane, where the wing of the aeroplane is on there. So we do the calculation using a finite element method. And in this method, the solution of differential equation, the homogeneous solution of the differential equation, we applied it, we calculate, we finish it using matrix analysis. So then we can found this kind of metric with the right hand side is 0. So then we finish it, find the eigenvectors or the eigenvalue, with the show the natural frequency of the system. To make sure that our calculation is correct, so in the first mode of the wet mode with condition, we applying the Kumai equation for 2-node vertical bending frequency. This formula is found by Pak Kumai. Is for the ship, every kind of ship, there's a float on the water, then the natural frequency can be approximated using their equation. It is also including the added mass for the calculation. The float construction itself, it consists of skin and bulkhead. This type of construction we taken from type of the SC6 Twin Otter, with the particularly the dimension of the aeroplane is almost similar to the N219 amphibian. And the float itself is made from carbon fiber reinforced plastic. Then we discretize this one using a 3D triangular element automatically. And the CFRP, we simplified the model using isotropic material. So then you can just apply the mass density, the material density of the CFRP average. Here, the calculation of model analysis is conducted in 3 conditions of the flood. We are dry condition, wet condition. In the wet condition, we have 2 conditions, the 0 and the forward speed. All the condition is we assume that, or we make it the seaplane with full load. It means with the mass of all passengers and goods are in the plane. Yeah. So in the dry mode solution, the homogeneous differential equation, the water inclusion is not observed. So we exclude the water. But in wet modes, the flow cell below waterline is compact with water. In this way, using parameter underwater float hull, the additional mass produced by the interaction between water and hull can be determined. The model of the effect forward speed of the float during taxiing on the water, especially at the landing one, because then we have the minimum and the maximum velocity speed of the seaplane when it will land on the water, using according to FAA regulation. This is the result you see here. This is with first mode, the dry mode. In the second mode, you see the first mode all with the same mode shape. But in the dry mode, especially in the highest mode, mode 3 is look like not same with the wet mode. The end of the float is the float shape is going up better than the dry mode, and in the going down for the dry mode. If you see the dry mode, sorry, in the wet mode of the Kumai, speed 0, 172.2.6. In wet mode is 72. In final element, we calculate is 172.9.9. It's almost close lah. Yeah. So you can see that it's okay, the modeling of finite element. From here, it is shown in table 1 before. The wet mode of the float approximate from finite element method is a good agreement with the Kumai method calculation. This means the numerical modeling using finite element is verified. The dry mode has also greater value than the wet mode. This is because added mass surrounding the float changes the characteristics of the vibration. Stiffness seems to become softer when wet due to the presence of the water. The model frequency at higher wet mode 3 and 4, show an significant frequency change of frequency. This could be the vibration of the float becoming stable for the high frequency. So it means when you have maybe vibration on the lower RPM, maybe when you go higher RPM of the engine, then you gone the vibration. When the float forward the speed, water surrounding the water of her also move. It will create dynamic pressure. This pressure lifts the whole body of the float in oscillatory motion. That may soften the stiffness of the float vibration system. Therefore, the wet mode frequency also decreases as the float speed forward. From there, we have the conclusion from this study. It has been found that the wet mode of the float approximate from finite element model is a good agreement with the Kumai method calculation. It showed that the frequency of the wet modes are lower than the dry modes. The wet mode frequency also decreases as the float speeds forward. From the computational result, it is clear that seaplane operation in the water has a significant role on the float structural dynamics, which should be considered in the normal modes prior to the whole system vibration analysis. These are some of our references that we made. I just want to show to you the number one, the references here for the CFRP, why we do the simplifying using isotropic, and the regulation from FAA. Also, the last one is the 13th one is the Vipire Inc. is a company that made floats in the world. I think number one. So they have so many examples of the float that they have already built and already installed in any types of seaplane. So this the acknowledgement. Of course, we are very appreciative of the research grant from the National Research and Innovation Agency Indonesia of this Aeronautic and Aerospace Research Center of Aeronautic Technology Research Program to conduct this study. And thank you. If you have any question, comment, or suggestion, please do not hesitate and to forward to us, come forward to us, and we are more than happy to answer if we can, and if not, then we are going to study together. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.